On the morning of December 14th, analysts reviewing overnight radio data noticed something they almost dismissed. At first glance, it looked like background interference, a faint irregularity sitting just above the cosmic noise floor. But when the data was isolated and slowed down, the anomaly refused to disappear. Instead, it revealed structure. This was not static. Unlike the chaotic hiss that usually dominates deep space frequencies, this signal showed restraint. It occupied a narrow band. It did not drift. It did not scatter. It repeated itself with deliberate spacing, rising gently, holding, then fading, only to return again, unchanged. The repetition was slow enough to feel intentional, yet subtle enough to hide among natural phenomena. Radio telescopes across multiple continents confirmed the same behavior. Each station detected the pulse independently, with no timing discrepancies that could suggest local interference. The source direction triangulated cleanly. Every path pointed back to the same object. 3I Atlas. What made the signal extraordinary was not its strength, but its discipline. Natural emissions in space fluctuate wildly. Plasma interactions spike, solar wind surges, charged particles scream across the spectrum. But this signal did none of that. It behaved as if it were regulated, constrained by an internal rule set. The pulse exhibited modulation, not random modulation, but layered. Each repetition carried slight internal variation, like nested waves stacked inside a larger envelope. When engineers stripped away the outer harmonic, a secondary rhythm emerged beneath it. When that rhythm was isolated, a third appeared. This was not noise. It was structure layered within structure. Scientists attempted to classify the emission using known astrophysical templates. Pulsars were ruled out immediately. Their emissions are sharp, violent, and rotational. Magnetars were dismissed just as quickly. Their signatures are chaotic and destructive. Even artificial satellites could not account for this behavior. The signal lacked Doppler drift, meaning it was compensating for motion. That detail alone changed everything. An object moving through space should produce a measurable frequency shift. Yet this signal maintained its pitch with uncanny precision. The only way to do that would be to actively adjust the emission in real time. Correcting for velocity and orientation, that is not something comets do. As researchers continued to examine the waveform, another detail emerged. The pulse spacing was not arbitrary. Each cycle returned after the same interval, with no cumulative error. Over hours of observation, the timing never slipped. Not once. Clocks drift. Systems decay. Even the most stable natural oscillations show variation over time. This one did not. Some scientists suggested that the signal might be a resonance effect, energy trapped within the object, ringing like a bell struck once long ago. But resonance fades. This did not. It held steady, as if continuously sustained. Others proposed that the pulse could be an echo, a reflection of something else, bouncing through the object's structure. But echoes distort. They weaken. They smear. This signal remained clean. What disturbed the teams most was not the pulse itself, but its restraint. It did not grow louder as 3I Atlas approached Earth. It did not escalate. It did not attempt to announce itself. It simply persisted, quiet, measured, patient. Almost as if it had been repeating for a very long time, and had no reason to stop now. By the end of the first analysis window, the conclusion was unavoidable. Whatever this signal was, it was not accidental. It was not a byproduct of heat, motion, or collision. It was deliberate. And if the signal was deliberate, then the next question became unavoidable as well. Who, or what, was it meant for? Once the modulated pulse was confirmed, attention shifted from the signal itself to the body that was producing it. If the emission was deliberate, then its source mattered more than its content, and that meant looking beyond the surface of 3I Atlas. Radar teams began reanalyzing reflection data that had previously been considered routine. Standard radar returns from comets are blunt. The signal hits the surface, scatters, and returns almost immediately, distorted by dust and irregular terrain. That was not what the data showed this time. Instead, the return signal came back in layers. The first reflection behaved as expected, bouncing cleanly off the outer shell. But milliseconds later, a second response arrived. Then a third. each weaker than the last, but still coherent. The timing gaps between these echoes were too wide to be surface irregularities, yet too consistent to be noise. The signal had gone inside. This was unexpected. Cometary bodies are porous, but not hollow in any organized way. Radar energy typically diffuses quickly through loosely packed ice and rock. It does not return structured echoes unless it encounters internal boundaries. And yet here they were. Engineers mapped the delays and reconstructed a three-dimensional model of the signal's path. What emerged was unsettling. The radar pulses appeared to be reflecting off an interior surface, not a chaotic mix of debris, but something smoother, more defined, almost symmetrical. This did not imply an empty cavity in the traditional sense. Rather, it suggested a region of contrasting density, an internal shell or chamber capable of reflecting energy rather than absorbing it. When those internal echoes were compared to the timing of the external modulated pulse, the correlation was immediate. Every internal reflection aligned with the pulse cycle, not loosely, exactly. It was as if the signal outside and the structure inside were locked together, functioning as part of the same system. One theory proposed that the object's interior could contain layered materials formed naturally under extreme interstellar conditions. Another suggested compression artifacts from ancient collisions. But neither explanation accounted for the precision of the echo timing. Natural formations do not produce synchronized internal reflections. More troubling was the behavior of the echoes over time. As observation continued, the delay between reflections subtly changed, not randomly, but proportionally to the object's orientation. When 3I Atlas rotated, the echo pattern adjusted. When it stabilized, the pattern stabilized too. This implied geometry, not fractured geometry, not chaotic voids, but a structured interior that responded predictably to motion. At this point, analysts attempted passive tomography, using background cosmic radiation instead of active radar. The results confirmed what the radar had hinted at. The interior of 3I Atlas was not uniform. It contained zones that bent energy rather than scattering it. And those zones appeared to be centered. The echoes were strongest when the radar path aligned with the same region that earlier optical instruments had identified as the source of the surface flicker. That convergence could not be ignored. Whatever was producing the signal was not spread throughout the object, it was centralized. The possibility of a naturally hollow comet core was considered, but such structures collapse under their own gravity over time. They fracture, they vent, they leave debris signatures. 3I Atlas showed none of that. No collapse, no fracture lines, no mass loss. Instead, the object behaved like a shell maintaining its integrity, preserving whatever lay within. Some scientists began referring to the internal echo zone as a resonant chamber, though no one could explain what it was resonating with. Others were more cautious, describing it as an anomalous density region pending further analysis. But the implication remained the same. The signal detected outside the object was not originating from random surface activity. It was emerging from inside. And if something inside 3I Atlas was producing a stable, compensated, repeating signal, while being protected by a structure capable of reflecting energy inward, then this was no longer a question of strange physics. It was a question of purpose. Because echoes do not exist without walls, and walls do not exist without design. With the discovery of internal echoes, scientists expected the signal behavior to remain stable. Instead, something unexpected happened. As the hours passed on the morning of December the 14th, the emission profile of 3I Atlas began to change. Not dramatically, quietly. The broad background glow that usually surrounds cometary objects started to thin. At first, it was barely noticeable, a slight reduction in bandwidth, a subtle tightening of frequencies that most automated systems would have ignored. But when analysts overlaid the new data on earlier recordings, the difference became clear. The spectrum was collapsing, inward. Normally, objects like 3I Atlas reflect and emit across a wide range of frequencies. Dust scatters light unpredictably. Gas fluoresces. Thermal radiation leaks outward unevenly. The result is a messy, wide spectrum that resists simplification, but now that messiness was disappearing. The outer frequencies faded first. High-energy noise dropped away, followed by the lower, more chaotic bands. What remained was a narrow core frequency that refused to disperse. It held steady, brightening not in strength, but in clarity. This narrowing was not passive. If the object were cooling or losing material, the spectrum would thin unevenly. Certain bands would spike, others would vanish. Instead, every reduction occurred symmetrically, as if guided by a rule rather than a reaction. One scientist described it as a system closing doors. As the emission band narrowed, background interference around the object also declined. Cosmic microwave noise dipped slightly within a defined radius. Not enough to be called suppression, but enough to be measured. It was as though the space immediately surrounding 3I Atlas had become quieter. That detail disturbed researchers more than the narrowing itself. Space does not quiet naturally. There is always noise, always radiation, always motion. For a region to show reduced interference suggested interaction. Something was shaping the environment around the object, even if only weakly. Meanwhile, the internal echoes detected earlier began to sharpen. The reflections became cleaner, less distorted. The echo paths aligned more tightly with the narrowed emission band, as if the object's interior and exterior were synchronizing. It no longer looked like a signal leaking outward. It looked like a signal being selected. Several teams attempted to model the phenomenon using natural explanations. One idea proposed that layered ice inside the comet was acting as a frequency filter. Another suggested that dust grains were aligning magnetically, suppressing certain wavelengths. But none of those explanations held up under scrutiny. Magnetic alignment would fluctuate with solar conditions. It did not. Dust filtering would scatter energy, not concentrate it, and layered ice would produce irregular attenuation, not clean spectral collapse. The narrowing continued. By mid-morning, nearly all emissions outside the core frequency had faded into background levels. The object now appeared quieter than surrounding space, except for the persistent pulse. And that pulse had changed. The internal modulation became more pronounced. The nested rhythms detected earlier separated further, becoming easier to distinguish. It was as if the signal was clearing space for itself, removing interference, simplifying the channel. Some researchers began to compare the behavior to bandwidth allocation in communication systems. When interference is high, systems widen their spread. When conditions stabilize, they narrow, focusing power where it matters. If that analogy held, then 3I Atlas was not just emitting, it was optimizing. The implications were unsettling. Optimization implies feedback. Feedback implies awareness of conditions, and awareness implies monitoring. At no point did the signal intensify to demand attention. It did not grow louder or faster, it simply became cleaner. That restraint mattered. If the purpose had been to announce itself, it could have done so easily. Instead, the object behaved like something waiting for the right conditions, reducing noise, refining output, and preparing the channel. By the end of the observation window, the conclusion was unavoidable. The signal was no longer fighting the environment, it was controlling it. And as the spectrum narrowed to its final quiet form, researchers were left with a chilling realization. This was not the beginning of the signal. This was the moment it chose to be heard. As observatories across the globe turned their focus to the evolving comet cluster, a new pattern emerged, one that defied randomness. What began as isolated behavior from a single core evolved into a collective rhythm. Instruments aboard the James Webb Space Telescope began to register recurring emissions of ultraviolet light, each spaced by a precise interval. At first, these pulses were dismissed as residual noise, artifacts from solar interference or sensor recalibration. But as more data was compiled, the rhythm persisted. It was too regular, too deliberate. Each core in the cluster began to emit in a tightly synchronized sequence, almost like a mechanical heartbeat radiating across astronomical distances. The timing between each pulse narrowed over time. It wasn't chaotic, it was converging. Researchers at Caltech developed a simulation to model the emissions, and what they found changed the tone of the entire mission. The pulses weren't just synchronized, they were adjusting themselves based on the comet's position relative to Earth and to each other. This meant one thing: feedback. Something within this comet chain was interpreting spatial variables and modifying behavior accordingly. The most plausible natural explanation involved gravitational resonance. Perhaps a shared orbit had created a tidal locking effect between cores. But that didn't explain the light emissions or their spectral composition. The pulses weren't simple bursts of energy. They were layered with fine-tuned frequencies, similar to those used in deep space communication experiments. Avi Loeb, observing from the Galileo project's private array, suggested the synchronization may reflect an underlying control system. If the objects were artificial or artificially enhanced, their behavior could resemble a protocol handshake, much like two satellites establishing link stability. NASA, however, remained cautious. Publicly, they referred to the emissions as electromagnetic harmonics potentially tied to magnetic dust alignment. But internally, their teams were scrambling. The harmonics were starting to line up with Earth-based time cycles. Each pulse now arrived during consistent Earth time intervals, regardless of rotation or orbit, a phenomenon that strongly suggested targeting calibration. One cycle aligned with sunrise over North America, another with midnight in Asia. These were not random points of reference. They were geospatial markers. The scientific community began to fracture into three camps. One side insisted on a natural explanation, gravitational resonance, solar wind interference, or layered crystallographic emission structures. The second group leaned toward technological augmentation, a possibility that these comets were seeded with synthetic materials that behaved predictably under cosmic radiation. And the third camp, growing quietly, believed in intentional design. If synchronization continued to tighten, it could signify the beginning of phase transitions, what engineers call activation thresholds. In systems theory, this is when distributed nodes begin to act as a singular entity. If these comets were aligning, synchronizing, and timing emissions, then the next logical step could be coordination. And if coordinated, who or what was giving the orders? The synchronized pulses had only just begun settling into rhythm when another anomaly emerged, this time involving motion. NASA's Deep Space Network, in tandem with the European Space Agency's Gaia Observatory, began detecting an unexpected deceleration within the cluster. Not a uniform one, but a directional slowdown. Specifically, the cores furthest ahead in the formation began to lose velocity along their heliocentric vector, while those trailing behind maintained course. This behavior went against the grain of all known cometary dynamics. Natural deceleration typically occurs due to solar radiation drag, sublimation, or gravitational interaction with nearby bodies. Yet none of these factors were sufficient to explain the current readings. The slowdown was precise, controlled. The forward objects were not simply drifting, they were easing back. Avi Loeb publicly commented that this mirrored something seen in spaceflight maneuvering, a deceleration maneuver known as orbital braking. In that context, it is used to reduce velocity ahead of insertion into a stable orbit, or to create intentional regrouping. Could the leading cores be waiting for the others to catch up? If so, this raised a new set of questions. Was the cluster adjusting to maintain spatial integrity as it approached the inner solar system? Or was it responding to something external, perhaps scanning, perhaps steering? Either way, the evidence pointed to a level of intercore awareness. This was supported by another data point. The leading core, which had initiated the slowdown, also happened to be the same one responsible for the most recent polarization burst. Could it be acting as a leader? The European Southern Observatory released a classified report, later leaked, noting that the slowdown matched previous models of probe formations preparing for Earth flybys. These models had been used during planning simulations for missions like ESA's JUICE or NASA's Lucy. And now, eerily, the cometary cluster appeared to be mimicking them. What puzzled everyone was the mechanism. Comets, even the most massive ones, are not known to self-regulate speed. There was no visible outgassing, no dust jets acting as natural brakes. No solar slingshot event had occurred. The objects simply began to slow, gradually, but measurably. It was during this phase that Chinese telescopes reported a secondary anomaly, a faint ion trail behind the leading object, just enough to suggest propulsion. Not outgassing in the traditional sense, but a narrowly focused discharge of particles. The stream was so fine it barely registered on standard instruments, but when isolated it formed a perfect line opposite the vector of motion. A propulsion trail. NASA downplayed the reports, citing possible sensor artifacts, but international observatories weren't convinced. The trajectory models were now diverging. Projections showed that should the slowdown continue, the cluster could begin reorienting, shifting not around the Sun, but toward a direct Earth intercept vector. If the forward objects were waiting, and the rest were catching up, then the final outcome could be a unified flyby, or worse, a structured arrival, and for the first time, language changed inside mission reports. The word comet began to appear in quotation marks. What first appeared as a diffuse, chaotic cloud around 3I Atlas quickly revealed something far more deliberate. When the dust halo was analysed using adaptive optics and multispectrum layering, it no longer looked random. In fact, it didn't even look like a traditional coma. Instead of a spherical dispersion, the kind produced when solar heat sublimates surface ice, the dust around 3I Atlas followed angular planes. Sharp geometric corridors of particles extended from its equatorial region, forming what one astrophysicist described as a segmented shell. Each segment seemed to emit in a different infrared profile. Some were cooler, some radiated more intensely, and others showed almost no thermal signature at all, like cold voids embedded in the dust itself. That wasn't normal. In typical comets, heat spreads more or less evenly across the dust cloud, but this looked partitioned, and the symmetry was too perfect to ignore. There were 6 primary lobes, spaced almost exactly 60 degrees apart in orbital cross-section. When mapped, they formed what looked like a hexagonal array, a halo with a clear modular structure. The James Webb Space Telescope confirmed the shape by capturing backscatter from solar radiation at a wavelength near 10 microns. The reflected light wasn't diffused. It came back in repeating wavefronts, almost like signal beams, bouncing off facets. This led one group of researchers to model the dust halo as a phase diffraction grid. In simpler terms, the halo wasn't just made of dust, it might be controlling light. If true, that would change everything. A shaped halo implies the ability to mask or redirect electromagnetic signatures, something no known comet has ever done. And it could explain why certain ground-based observatories were briefly unable to lock onto 3I Atlas at all, even when it was supposedly in view. The geometry also shifted with time. Over 3 consecutive days, the angles of the halo lobes began to tilt, but not randomly. Each tilt was time-locked to 3I Atlas's rotation rate, like gears clicking into place. And yet, the strangest discovery came not from deep space telescopes, but from amateur astronomers. When they photographed the halo through modified ultraviolet filters, they captured interference patterns, waves, echoes, and in the center, a ring of perfect darkness, completely absent of scatter or emission. Scientists are now calling this the zero shadow zone. It acts like a null point, absorbing energy or bending it around itself. Either possibility raises the disturbing question: is this region engineered? Because in cosmic terms, natural systems prefer entropy. But what 3I Atlas is doing, it looks like design. The dust halo isn't just decoration. It may be a shell, or a signal carrier, or something else entirely. As observatories continued monitoring 3I Atlas, another surprise emerged, one that couldn't be explained by light or dust. It was magnetic, and it was local. The first hints came from magnetometer data on board the solar orbiter. During its standard pass near the orbital path of 3I Atlas, the probe picked up a mild but distinct magnetic anomaly. It wasn't strong, nowhere near what a planet or even a magnetized asteroid would emit, but it was directional, focused. It pulsed in a pattern that suggested coherence, not randomness. Initially dismissed as instrumentation error, the reading gained credibility when the Parker Solar Probe, passing through a completely different part of the inner system, detected the same rhythm. A 3-phase pulse, occurring every 17 minutes and 22 seconds. Always identical, always clean. The magnetic signal didn't match anything emitted by the Sun or known heliospheric disturbances. It was too quiet, too consistent. But most importantly, it aligned with the vector of 3I Atlas's approach. As it passed into Earth-observable range, radio astronomers at Arecibo's successor arrays began to notice interference not in their data, but in the structure of the incoming signals. Faint modulations just above background noise would rise and fall in synchrony with 3I Atlas's position relative to the solar wind. When plotted across time, those modulations formed a waveform that wasn't static. It evolved. It curved into loops, crossed its own axis, and eventually spiraled into what one physicist called a self-similar magnetic map. That map wasn't just a trace, it was directional. It suggested a field aligned to specific objects, namely the clustered comets deployed around 3I Atlas. One signal seemed to ping-pong between these comets, creating a soft magnetic corridor. Within that corridor, solar particles behaved strangely, protons slowed, and electron density shifted. The usual rules of diffusion didn't apply. Something was shaping the solar wind itself. The implications are enormous. If the objects around 3I Atlas are generating localized magnetic fields, they're doing it in an environment that should destabilize such fields instantly. The solar wind is chaotic, fast-moving, and high temperature, but these fields were stable. More unsettling, the field lines weren't radial, they wrapped. In some areas, they even curved backward, defying the solar wind's flow. That only happens in magnetically confined plasma environments, like inside reactors or engineered systems. The leading theory is that these fields aren't side effects of the comet's movement. They are tools, perhaps for shielding, perhaps for communication, or, some now suggest, navigation. Because once again the magnetic pulses began to match the movement of the synchronized comet cluster. Every directional slowdown, every microjet ignition, occurred right after a spike in magnetic activity. It's not just light, not just dust. 3I Atlas may be talking in magnetism, and Earth, for the first time, is listening. Most comets are chaotic on the outside, pitted ice, jagged rock, random fractures sculpted by centuries of solar heating. But the surface of 3I Atlas didn't look like that. Not at all. When NASA released enhanced spectral maps gathered from narrowband imaging, a strange truth emerged. The surface was smooth, but not smooth in the way worn asteroids are. This smoothness had pattern, linear textures that repeated across equatorial regions, forming ridges and grooves that ran almost parallel like engineered lanes. Even more startling was the reflectivity. Specific sections of 3I Atlas's sun-facing hemisphere exhibited an albedo curve far higher than anticipated. Not only was it more reflective than expected, it fluctuated based on wavelength. In visible light, it behaved like dirty ice, but in near-infrared and ultraviolet, it bounced light like polished composite. Some areas seemed to phase in and out of visibility entirely under different filters. That's not typical of any known celestial body. Scientists propose this could be due to a metamaterial-like structure, a surface layer that responds to radiation by altering its transparency or reflectivity. A closer inspection revealed thermal scars. These were narrow bands along the mid-latitudes where the surface radiated heat disproportionately, while adjacent areas stayed cold. There were no visible eruptions, no dust plumes, and no gas jets from these zones. Yet heat pulsed out of them in a regular cycle. That's where the data broke the models. For these scars to emit heat without ejecting material suggests internal conduction, an engineered conduit system or buried network that moves thermal energy across the body's surface in non-random ways. But then came the polar readings. Both poles of 3I Atlas, unlike typical comets, showed complete inertness. No activity, no brightness spikes, no outgassing, nothing. Instead, they were ringed by concentric thermal depressions, zones where heat was being actively suppressed or absorbed. The ESA's spectrometer arrays flagged these zones as negative emissions, a classification usually reserved for artificial sensors or cloaking systems on Earth satellites. It didn't make sense, unless, of course, something on 3I Atlas was regulating its own thermal footprint, minimizing detectability. In ultraviolet imaging, one section of the surface even displayed a radial glow, like a flower petal unfurling from the nucleus. The symmetry was uncanny. This glow pulsed at low frequency, not tied to rotation, suggesting something buried beneath the surface was rhythmically activating. The key question emerged: what are we actually looking at? Because the surface of 3I Atlas doesn't just reflect light, it reacts to it, it manages it, and that opens the door to a possibility that many had previously dismissed as fringe, that the body isn't inert, that it's doing something, responding, regulating, preparing. When the first rhythmic pulses were detected, most assumed they were noise, weak short-duration radio fluctuations, nothing that looked like intelligent signaling. But over time, as 3I Atlas came into tighter observational range, the pattern became undeniable. It was repeating, and it was precise. Every 23 minutes and 41 seconds, a low-frequency emission emerged from the core trajectory of 3I Atlas. It wasn't loud, and it wasn't modulated in the way typical communication systems operate. But its repetition and duration never drifted. Even as the comet altered speed or shifted its alignment relative to the Sun, the signal held. Ground-based radio telescopes in Australia and Chile began logging the emissions around the clock. What they found next pushed the phenomenon into international spotlight. The pulse coincided with minor trajectory adjustments, small course corrections made by the clustered objects moving around 3I Atlas. Each time the signal fired, at least one object in the swarm subtly changed position. Sometimes it was a drift of only a few kilometres. Other times it was a burst of motion, as if responding to command. When plotted against time, a pattern emerged. The control pulse didn't just tell the swarm when to move, it dictated which one moved, where and how fast. It was a control network, a central broadcaster managing a coordinated fleet. This pulse wasn't electromagnetic noise, it was architecture. Theories emerged rapidly. Some proposed it was gravitational micromodulation, an advanced form of using internal mass shifts to broadcast information through tiny gravitational nudges. Others leaned toward magnetoacoustic signaling, using oscillating fields to encode movement instructions. Still others suggested something far simpler, like short-range directional jets being triggered by internal logic boards or central guidance systems. Whatever the mechanism, the effect was real. This control pulse was measurable. It was targeting specific companion comets, and its repetition was the glue holding the entire formation together. But then something changed. 2 days after the Moon passed through 3I Atlas's vector corridor, the pulse shifted frequency by only 0.1 Hz, but enough to alter the energy pattern. The swarm briefly destabilized. Objects wobbled and one even entered a slow spiral, and then the frequency corrected. The formation realigned, and a second pulse, shorter, sharper, was introduced. Dual frequency signaling, like switching from Morse code to encrypted binary. That's when researchers proposed a chilling new idea. The control pulse might be adaptive. It might be learning. If the timing, shape and reaction of the swarm adjust in response to environmental variables, lunar gravity, solar wind turbulence, Earth's magnetic field, then it's not just being controlled, it's being piloted, and whoever, or whatever, is issuing that pulse from the core of 3I Atlas, it knows we're watching. In most known comets, thermal output varies wildly, especially during close solar passes. As sunlight bombards the irregular surface, some regions heat rapidly while others lag, producing erratic outgassing, chaotic rotation, and unpredictable energy release. But not with 3I Atlas. Thermal imaging from both ESA's Lagrange Point observatories and NASA's infrared tracking arrays revealed something that completely violated comet physics. 3I Atlas was maintaining uniform thermal output across nearly all latitudes and longitudes, even as it rotated, even as it entered different angular exposures to solar radiation. This meant one thing: the object was regulating its own temperature, deliberately. Infrared spectrometers logged surface temperatures fluctuating only within a narrow band of 4 degrees Kelvin across a 20-hour observation window. That's unheard of in natural bodies of this size and exposure. A comet of this magnitude should be shedding heat at uneven rates, spiking, plateauing and dropping depending on solar angle, surface material and internal structure. Instead, 3I Atlas behaved like a thermal capacitor. It absorbed energy and slowly re-radiated it in a measured, controlled manner. No flash heating, no surface volatility, no runaway thermal breakdown. Even stranger was the directional symmetry of its emission. Instruments detected identical thermal signatures on opposing hemispheres, north and south poles, east and west quadrants, as if the body were not a chaotic rock but a balanced machine, designed to achieve stasis regardless of external pressure. Then came the high-frequency thermal pulses. These were microbursts of elevated radiation, localized to specific equatorial scars visible in earlier surface scans. They emerged on a timer every 7.2 hours, lasting for just under 12 seconds, then returning to baseline. Their wavelength was consistent, their magnitude modest, but the precision of their timing was unnerving. Theories poured in. Some believed this was heat being vented from an internal core through a controlled cycle, similar to radiative cooling on spacecraft. Others argued these bursts were evidence of onboard computation, localized hotspots tied to embedded energy systems. Still others proposed a more radical idea, that the thermal uniformity was being externally maintained by a swarm of companion objects. In this view, the entire cluster functioned like a distributed radiator, working together to absorb, balance, and emit heat in synchronization, using the central mass as the anchor. Whatever the mechanism, the implications were enormous. If a body could retain its thermal balance despite gravitational pulls, solar flares, and chaotic dust drag, then it wasn't behaving like any comet we've studied. It was functioning like a craft, not necessarily piloted, not necessarily crewed, but engineered to maintain environmental equilibrium. That's when an overlooked detail in the NASA log files became public. During the closest thermal flyby, a probe reported the exact same infrared temperature from 5 separate angles, some of them obscured by shadow. That's impossible. You can't get identical heat readings from a sunlit surface and a shaded crater unless the surface is emitting heat evenly, or it's being actively managed. And if 3I Atlas is managing its own temperature this closely, then it's doing so for a reason. The moment scientists confirmed that 3I Atlas had altered its drift vector without any visible outgassing, a single question echoed across every mission control room. How? Comets drift due to non-gravitational forces, usually jets of vaporized material erupting as the sun warms volatile compounds beneath the surface. This jetting changes trajectory over time, sometimes subtly, sometimes dramatically. But in the case of 3I Atlas, there was no such activity, no visible plume, no sudden outburst, no rotational tumble, yet it shifted course. High-precision orbital telemetry showed that 3I Atlas deviated from its projected trajectory by over 2,000 kilometers over a 48-hour period, beginning subtly, then accelerating in precision-corrected increments. The deviation wasn't chaotic. It wasn't the kind of random wobble you'd expect from a melting chunk of ice. It was surgical. The shift aligned the object closer to a point in space recently vacated by a companion body, a smaller, fast-moving object that had earlier passed between Mars and Earth. It appeared as though 3I Atlas was rendezvousing, coordinating, matching path lines with another piece of the swarm. Orbital analysts ruled out gravitational assists. No planetary body or large moon was near enough to cause the shift. Solar wind, insufficient pressure, radiation pressure, negligible impact. What remained was either mass redistribution or internal thrust, both highly advanced for a natural body. That's when the Doppler readings changed. As Earth base stations began logging the object's reflected signal, slight asymmetries began to appear in the redshift curve. These weren't due to velocity change alone, but to rotational drift. The body was subtly rotating opposite its new drift, like a swimmer angling their shoulders to steer through a current. This suggested intentional vectoring. Something inside the object was manipulating its moment of inertia, either by shifting mass internally, like a reaction wheel, or by emitting microjets too faint to see, but sufficient to nudge its path. NASA's deep space analysts proposed that the core may be laced with adjustable ballast, dense material that can be moved along internal tracks to alter center of mass. Others speculated on electromagnetic steering, using interactions with the solar magnetic field to generate torque. But then a shock came from the ESA's Silent Observer satellite near L1. The satellite recorded a slight oscillation in the local spacetime curvature around 3I Atlas during its drift. The ripple was too weak to be gravitational, but too structured to be random noise. It was as if space itself had been gently nudged in a specific direction. If confirmed, this would be the first time a non-terrestrial object exhibited behavior resembling inertial damping, a phenomenon theorized in advanced propulsion models but never observed in nature. It's still unclear what powered the course correction, but the fact remains. 3I Atlas changed direction, not because of chaos, not because of collapse, but with deliberation, with coordination. And if a comet can realign itself without jets, without plumes, and without visible propulsion, then it's not a comet. It's something else. Among the most unsettling observations of 3I Atlas came not from spectroscopy or trajectory analysis, but from something far more visual, an intermittent internal glow observed deep within the object's core. It was first spotted by the Hubble Space Telescope, which had been programmed to monitor 3I Atlas during a low reflectivity phase. Analysts expected to record standard surface dimming as the comet rotated, but instead, something strange emerged. A flicker, located not on the surface but beneath it, originating from what appeared to be a central cavity. This wasn't a thermal emission. It wasn't infrared. It was faintly visible in the deep red and near-infrared range, emerging in rhythmic pulses like a heartbeat. But most disturbingly, it was patterned. Over a 6-hour observation session, Hubble recorded the flicker repeating at precise intervals. Every 77 seconds it would glow, then vanish, then return, and vanish again. The pulse remained stable, consistent, and unaffected by rotation, solar proximity, or external dust conditions. NASA and ESA teams reviewed the footage side by side with earlier scans from the James Webb Space Telescope. To their shock, JWST had also recorded the same flicker, weeks prior, but only in short bursts and at a lower intensity. This suggested the phenomenon was strengthening over time, as if the core was powering up or broadcasting. The structure of the light itself was even more intriguing. Advanced analysis showed that the flicker wasn't spherical or diffuse. It emanated in a hexagonal shape, multiple edges, sharp corners, and stable geometry, something no known natural emission could produce. This forced a reclassification of the object's core. It could no longer be considered an amorphous frozen interior. The geometry implied internal architecture, or, at minimum, a containment field with engineered boundaries. Speculation exploded. Some researchers suggested this was a form of internal fusion, or energy cycling, akin to a controlled reactor releasing pulses through cracks in the crust. Others believed the pulses were intentional broadcasts, potentially data, information, or signalling mechanisms meant for other objects in the 3i swarm. One fringe paper even hypothesized that this was the first visual confirmation of core intelligence, a distributed AI system embedded within the comet's structure, waking in stages as it neared its programmed targets. Supporting this theory, ground-based interferometers detected microshifts in surrounding plasma activity each time the flicker occurred. Space didn't just glow, it responded. There were ripples, like something was emitting a wave through the vacuum itself, subtly altering nearby ion activity. By the time the object crossed Mars's orbit, the flicker had doubled in intensity. Even skeptics could no longer dismiss it as coincidence, and if this object's core was flickering with precision, stability and geometry, it meant the center wasn't chaotic, it was active, alive in a mechanical sense. Which raised the most terrifying possibility of all. The core was not simply a power source, it was a control center. Up until now, 3i Atlas had emitted a wide range of light and radio wavelengths, typical for large cometary bodies interacting with solar radiation. But as it neared the orbital plane of Earth, something unprecedented happened. The spectrum began to narrow. This wasn't a temporary shift. It was a complete reconfiguration of emission behavior. Using an array of telescopes across 6 continents, scientists began compiling spectra from the object's dust, gas, and core flicker. What they discovered was a progressive elimination of specific bands, hydrogen alpha emissions, vanished. Then several oxygen lines. Eventually only a tight band of wavelengths remained, centered around a frequency rarely observed in comets, 1420 MHz. That frequency is no coincidence. It's known as the hydrogen line, the universal signal proposed by scientists as the best frequency for intelligent communication in the galaxy. It cuts through cosmic noise, it's protected from natural interference, and more importantly, it's deliberate. 3i Atlas was now broadcasting almost exclusively on that line. This immediately triggered alerts within SETI, the search for extraterrestrial intelligence. Every telescope tuned to the hydrogen line began pointing toward the object, scanning for modulation, rhythm, or coded patterns. And while no clear message emerged, the intensity and clarity of the band were undeniable. Natural objects don't collapse their emissions like this. They don't choose a single frequency unless there's a mechanism involved. Further complicating matters, radio astronomers observed modulation drift, a slow cycling of signal amplitude and waveform complexity. It was as though the comet was adjusting its transmission, scanning, syncing, calibrating. The team at Jodrell Bank compared the signal to earlier fast radio bursts, FRBs, and noticed overlapping harmonic structures. Though weaker than typical FRBs, the timing and frequency spread resembled controlled pulses, not explosive events. In parallel, visible light from the comet dimmed, not because the object was losing mass, but because it was absorbing more and emitting less. focusing its energy into the narrowband transmission. This was interpreted by some as a cloaking measure, while others viewed it as signal prioritization, and that's when the alignment happened. On December 12th, the spectral beam aligned with Earth's equatorial rotation, maintaining lock for a full 3 hours. This wasn't random. The beam tracked Earth's orientation. It corrected for rotation. It followed us. Astrophysicists were stunned. The beam was not wide, diffuse, or wandering. It was tightly focused, just wide enough to cover the planet's diameter and steady enough to suggest stabilization algorithms. What was being transmitted remains unclear. No direct information has been decoded, but one thing is certain. The comet stopped being a passive object. It narrowed its emissions, focused its energy, and pointed itself at Earth, using the most universally significant frequency in radio astronomy. And that is not a coincidence. Comets are volatile by nature. As they near the Sun, their surfaces heat up rapidly, shedding dust, ice, and gases in chaotic waves. But with 3I Atlas, something broke the model. Instead of rising continuously, its surface temperature hit a precise plateau, then held. Sensors aboard the ESA's solar orbiter, which had been trailing the object's trajectory at a safe distance, picked up the anomaly first. They recorded the comet's surface heating at expected rates until it reached a threshold of minus 72 degrees Celsius. Then, nothing. No further change. No response to increased solar intensity. No thermal spike. The object had stabilized. At first, scientists attributed this to an insulating layer, perhaps a crust of super-dense material, but infrared mapping showed no buildup of thermal resistance. In fact, some areas continued to absorb solar energy at high rates, yet emitted no excess heat. The object was not insulating. It was regulating. More astonishing still, the plateau held across both illuminated and shadowed regions. It didn't matter if a surface was in direct sunlight or rotated into darkness. Its temperature clung tightly to the same baseline, as if governed by an internal thermostat. That shattered conventional comet physics. Researchers began reviewing comparative data from known interstellar objects, like Oumuamua and Tsai-Borisov, but none of them demonstrated this thermal behavior. Those bodies had wild fluctuations in surface temperature depending on composition, spin rate, and proximity to the Sun. But 3I Atlas was uniform, almost engineered. The consistency also extended to subsurface layers. Using polarized radiometric scans, the James Webb Space Telescope detected identical temperature plateaus as deep as 30 meters below the crust. This wasn't just a surface shell. It was a deep, stable thermal field. That's when theories began to shift. Was the plateau the result of internal power management? Could the object be cycling energy away from the surface and channeling it inward for a purpose? Some speculated it was rerouting thermal energy into propulsion or onboard systems, just as a spacecraft diverts solar energy into its engines or sensors. Others proposed that the object had entered a stealth phase, intentionally suppressing its radiative signature to confuse observers. But one clue stood out. At the exact moment the temperature plateau initiated, the narrowband hydrogen line signal intensified by 27%. That suggested coordination. Temperature and transmission were not separate events. They were likely part of the same system response, a shift in phase, a mode change, and perhaps most unsettlingly, the plateau persisted even during microsolar flares. The Sun launched a brief coronal mass ejection, CME, that swept through the region, but 3I Atlas's surface didn't spike, didn't dim, didn't budge. It ignored the solar storm entirely. That kind of resilience isn't natural. It's adaptive. It means 3I Atlas doesn't just survive the Sun, it manages its exposure like a vessel preparing for long-range interaction. Which leaves Earth with a disturbing question. What else is it managing? Just when researchers thought the thermal plateau was the peak of 3I Atlas's anomalies, a new phenomenon emerged, one that defied both cometary behavior and fundamental physics. It began with a burst. On December 13th, just after the object entered its fifth observational quadrant from Earth's perspective, NASA's Parker Solar Probe detected a high-velocity emission not aimed toward the Sun, as expected, but directly away from it. This stream wasn't a solar wind response. It was a structured jet, launched intentionally from the dark side of the object. Comets typically expel material as they heat up, creating solar-facing tails that blow outward in reaction to radiation pressure. But this was different. 3i Atlas was emitting jets from its shadow side, in a perfect anti-solar direction. At first, analysts believed this could be a byproduct of spin, maybe a delayed thermal reaction. But time-synced imagery from the Solar Dynamics Observatory revealed something else. The jets weren't passive, they fired in timed pulses. Roughly every 11 minutes, a narrow beam of high-energy plasma shot from a fixed point on the object's surface, always opposite the Sun. The composition of the jets further deepened the mystery. Spectroscopy showed they weren't composed of typical cometary materials like carbon monoxide or water vapor. Instead, they were rich in exotic ions, magnesium iron silicates, charged titanium particles, and trace amounts of iridium. These are not common in comets. In fact, iridium is more often associated with artificial impact signatures on Earth. Even more alarming, the jets maintained a coherent stream over 400 kilometers in length. Not diffused, not random. They were collimated, a term used in engineering for controlled straight-line beams like those found in propulsion systems. By now, one theory began to dominate. 3i Atlas was not ejecting material, it was maneuvering. The anti-solar jets resembled low-thrust propulsion systems observed in theoretical nuclear-electric spacecraft models. They expelled mass to adjust velocity, precisely, consistently, and deliberately. Simulations conducted at Caltech showed that if these jets continued firing at their current rate, the object would undergo a subtle course correction, just enough to intersect a new trajectory, one that pointed closer to Earth's orbital path. That changed everything. The object was not on a passive inbound drift. It was under guidance, its path was dynamic, and its propulsion method was unlike anything the solar system had encountered before. Astrophysicists tried to model the source of energy needed to maintain these anti-solar jets. The conclusion? A stable, long-duration power source must be operating from within the core, possibly fusion-based, or tapping unknown electromagnetic fields. And then came the strange part. Each time the jet fired, a low-frequency hum echoed in the radio spectrum. Not noise, not interference. A tonal signature, repeating at 73.1 Hz, detectable by both Earth-based receivers and the Voyager 1 probe still on the edge of interstellar space. It was as if the jets weren't just propelling the object, they were signaling with rhythm, like footsteps, intentional, measurable, and marching toward something. For decades, astronomers have relied on the way light reflects off an object to infer its shape, spin, and surface features. It's a simple equation. A round, natural object reflects light in predictable patterns. But the moment NASA's NEOWISE system began mapping the surface of 3i Atlas using reflected solar rays, the numbers fell apart. Reflected light didn't behave naturally. It aligned, sharply. Instead of scattering in soft gradients across the curved surface of the object, sunlight bounced off 3i Atlas in geometric sheets. Sharp, angular reflections emerged, flat planes of light that extended and faded with unnatural precision. It was as if portions of the comet's surface were engineered to function like polished facets, mirror-like structures placed intentionally across its shell. At first, some speculated these might be ice patches. Ice can reflect sunlight if exposed at the right angle. But when the James Webb Space Telescope analyzed those regions in the infrared spectrum, the answer came back. No ice detected. The material was dry, ultra-reflective, and unusually uniform in molecular structure. Then came the bigger anomaly. As 3i Atlas rotated, the reflected light didn't follow a chaotic pattern, like most comets or asteroids. Instead, the reflections synchronized with the object's spin axis, creating repeating pulses every 18.2 minutes. The reflective geometry wasn't a side effect, it was a function, a design. This caught the attention of the team behind the ESA's Lagrange mission. They began modeling the reflected light patterns as though they were part of a rotating signal array, something akin to a heliostat or a phased mirror array. The results were chilling. The patterns resembled an information cascade, as if sunlight was being used to transmit directional data across space. In simpler terms, sunlight in, message out. If that's true, then 3i Atlas isn't just reflecting light, it's modulating it. Every time a plane of light sweeps toward Earth, ground-based observatories pick up micro-variations in amplitude and frequency. Not random, but encoded. The math behind those light pulses matches known digital encoding schemes used in radio communication. It's not a perfect match to human protocols, but it's structured, organised, intentional. Several physicists now propose that the reflective geometry might be the comet's primary form of long-range communication, a solar-powered transmission system visible across millions of kilometres. And if Earth can detect these patterns, so can any object positioned at the Lagrange points, or even on the Moon. But perhaps the most unnerving part, this geometry only appeared after the anti-solar jets began firing, meaning it didn't always exist. It was activated. 3i Atlas may have shifted from passive observation to active transmission, using its angular reflective panels to signal, encode, or even respond to something. One astrophysicist described it bluntly: this isn't random reflection, it's geometry with a purpose. Every comet that nears a star faces the same fate: fragmentation. The sun's intense radiation, heat, and gravitational forces exert tidal pressures that rip apart unstable bodies. It's why scientists closely monitor each comet's integrity as it swings past the inner solar system. But 3i Atlas broke that model. Again, no cracks, no fissures, no plume of trailing debris, nothing. From its close approach to the Sun to its gravitational assist past Jupiter, not a single sign of stress or fragmentation was observed, and that shouldn't be possible. Based on its mass, velocity, and radiant exposure, multiple models predicted at least a partial break in the crust. Instead, the object held together with absolute structural coherence. NASA's ESOHO observatory tracked 3i Atlas through a coronal stream, an event that caused similar objects like Comet Encke and Ison to fracture or vaporize in past years. But 3i Atlas emerged unscathed. More than that, it appeared stronger. That raised urgent questions. Was this an unusually dense comet? Spectrometry suggested otherwise. Its overall mass density was surprisingly low, more in line with porous ice bodies than metallic asteroids, yet structurally it behaved like forged steel. That contradiction forced astronomers to consider a different explanation: internal reinforcement. High-resolution scans of its rotational dynamics revealed a startling possibility. The object's angular momentum remained perfectly constant, even under variable gravitational conditions. Normally, comets wobble or precess, tiny shifts in spin that indicate structural flexing. But 3i Atlas's rotation was locked, like a gyroscope held by internal supports. That's when the term monolithic frame entered the conversation. If this object has an internal chassis, rigid supports beneath the outer shell, then it's not a natural body, it's a construct. Some even suspect the surface may be deceptive, that the dusty outer crust is camouflage, a layer designed to mimic the appearance of a comet while hiding a far more resilient interior. This theory gained ground when ESA's Solar Watch Array detected multiple micro-impacts from meteoroids near the object's path, yet no response from the surface, no debris ejector, no craters, just absorption. It was as if the object shrugged off impacts like a bulletproof vest. To test this further, researchers simulated a collision model, predicting how 3i Atlas should fracture under standard impact velocities. The simulation failed. No input could produce fragmentation. The object absorbed and dissipated all energy below its surface without transferring stress to its core. The implications are vast. This means 3i Atlas can travel interstellar distances, survive near star passes, endure micrometeorite fields, and bypass gravitational stress, all without shedding mass. That's not a comet. That's an engineered traveller. And its silence, its lack of shedding, breaking or crumbling, is its loudest message yet. The instruments trained on 3i Atlas's tail began picking up something they weren't prepared for: a delay between changes in the core and the resulting reaction in its tail. Ordinarily, a comet's tail is a reactive structure, a responsive plume that aligns and dances according to solar radiation and the solar wind. It should react in real time. But on the morning of December 14th, that reaction didn't come instantly. It lagged. At first, it was dismissed as a calibration hiccup, perhaps a latency error in sensor data. But observatories cross-referenced their timestamps, and the numbers held. The core would emit a small pulse or shift in direction, and the tail wouldn't follow until several seconds, or even minutes later. In the vacuum of space, where cause and effect are direct and immediate, this delay was anomalous. One hypothesis emerged quickly and has now begun circulating more widely. The tail itself is no longer a passive reaction to solar forces, but an engineered structure. If the particles in the tail are being manipulated or channeled through some form of external field, perhaps magnetic or electrostatic, that would explain the delayed response. The tail would not be trailing freely, but would instead await a kind of activation command before it moved. Further complicating this theory is the shape of the tail. It has become increasingly symmetrical, at times even appearing as a split stream, almost like antennae rather than a dust cloud. Observers have noted how the tail flickers in discrete pulses, timed evenly. One astrophysicist described it as watching a flag that only flutters when waved at, not by the wind, but by a signal. This delay raises a deeper question. If the tail is not reactive but responsive, and responsive by delay, then something is receiving input before it acts. That implies reception, logic, and execution. And it points again to the same unsettling idea that keeps returning: control. If the tail is waiting to react, it's waiting for something. And if it's waiting for something, it's listening. The moment the polarization filter data started streaming in from the ESA's orbiting spectropolarimeter, the control rooms went quiet. What they saw was not just a repeating signal, it was a cycling pattern that reset itself every few minutes. The light waves bouncing off the dust, gas and ice around 3i Atlas were aligning in a rhythmic fashion. Not randomly, but in a rotating, repeating cycle. That's not how light scattering usually works in cometary environments. Under natural conditions, polarization tends to be noisy and chaotic, constantly shifting with outgassing events, solar flares, and solar wind turbulence. But what 3i Atlas showed was organized. The phase angle of its scattered light rotated methodically, not in the way a spinning object might cause, but in discrete steps. What makes this more compelling is that the cycle duration matched the radio burst timing picked up days earlier. Both patterns, in completely different spectrums, followed the same rhythm, a strange resonance across different data channels, one in light, one in frequency. Some suggested that the comet's surface might be covered in microcrystalline material, reflecting light in structured interference patterns. But that wouldn't explain the synchronization with radio bursts, or the angular precision in the rotation. Others proposed that this polarization cycling could be a form of optical signaling, a visual broadcast of information encoded in the spin of reflected light. If that's true, the implications are staggering. It would mean that we are observing a communication mechanism that operates in a format both visible and directional. Not noise, not radiation, but broadcast. The repeating polarization loop resets every 4 minutes and then begins again. Always the same order, always the same phase curve, no randomness, no decay, only persistence. Whatever 3i Atlas is, it is not hiding anymore. It's reflecting more than sunlight. It's reflecting intention. On the morning of December 14th, a high-resolution composite from the Lagrange 2 array revealed something unexpected. Not within 3i Atlas itself, but just behind it. Nestled in the comet's trajectory arc, barely distinguishable from background noise, was a dim object with a faint thermal signature. At first, it looked like a drifting ice shard or a trailing fragment. But it wasn't trailing, it was escorting. This was not the first time multiple objects had been associated with 3i Atlas. Earlier fragments had been detected and dismissed as debris, but this one behaved differently. It matched 3i Atlas's velocity perfectly, it curved with it, and most importantly, it adjusted position before 3i Atlas changed its own, as if anticipating a shift, as if leading. Within hours, the team unofficially named it the sixth object. 5 others had been loosely catalogued in previous weeks, but all showed erratic motion. This one was stable, directed, geometrically offset by a constant angle, 31 degrees from the main body. Over multiple rotations, it never deviated. Some analysts proposed that it might be a control node, a kind of gravitational reference or an external relay. Others suggested it was an autonomous fragment, possibly ejected earlier and maintaining a fixed distance due to synchronized inertia. But one unsettling possibility began to circulate through private channels. this sixth object was guiding 3I Atlas, not following it. This interpretation gained traction after a comparative Doppler analysis showed that the sixth object initiated movement patterns that were then mirrored by 3I Atlas seconds later. The implication was clear: the main comet was reacting to its smaller companion. For something of that scale to have priority in a gravitational pair, it would have to possess not just mass, but control. And if the smaller object is piloting the larger one, then this changes everything about how we interpret 3I Atlas. It is no longer a solitary traveller, it is part of a formation, a quiet, precise formation moving closer to Earth. Up to this point, every model, every orbital map, and every vector simulation had comfortably shown 3I Atlas bypassing Earth. Even with its bizarre behaviour, flickering jets, synchronized tail delays, core flickers, it was always projected to sail past. Until today. A new convergence model, built from updated trajectory inputs, began displaying a slow, persistent shift. It wasn't abrupt or catastrophic. It was subtle, like a drifting car correcting its steering wheel 1 degree at a time. But across millions of kilometres, even a single degree matters. For the first time, the relative path between Earth and 3I Atlas is tightening. The ESA's orbital probability envelope has narrowed from wide arcs into a clustered corridor that brushes Earth's orbital plane more closely than anything in the last 5 weeks. Not a collision course, yet, but converging, predictably. The anomaly? There's no gravitational reason for this. No nearby planetary mass, no sudden thermal jet that could explain the shift. The change is directional, almost navigational, as though something internal to 3I Atlas, or external via the sixth object, is applying course corrections. This theory is made worse by the time signature. The convergence began precisely 4 hours after the appearance of the sixth object. That's not random, that's cause and effect. Astronomers are now split. Some still claim this is within natural comet variability, that volatile jets can create course drift. Others are growing quiet, observing more than speaking. But a few, including former orbital mechanics experts, have gone further. They've started modelling this behaviour as if the object was aware of Earth's position, not colliding, not evasive, just approaching. And if the trajectory continues on this curve, 3I Atlas will pass through Earth's magnetotail at an angle that aligns with its anti-solar jets. That kind of intersection isn't just close, it's symbolic, like a key slotting into a lock. The question that remains isn't just how close it will come, it's why it would want to. It started as a pattern, faint, symmetrical, and nearly dismissed as a pixel artifact. A wide-field composite from the Hawaii-based infrared array revealed something that had never been seen before inside any known cometary structure, repeating radial formations inside 3I Atlas's active zone. Not streaks, not debris spirals, but nested geometric rings, evenly spaced and rotating out of phase with the nucleus. When the data was scrubbed and reanalyzed, from 2 different instruments, one infrared, one polarized optical, the same structure emerged. These were not natural. Their spacing followed the Fibonacci sequence. Their reflectivity oscillated at a precise harmonic. Their alignment pointed not away from the sun but toward Earth. And then came the telemetry spike. Not from 3I Atlas directly, but from high-frequency antennas pointed at its dust field. A signal, buried beneath the dust halo, modulated across a narrow-band spectrum just above the cosmic microwave background. It pulsed at a mathematically perfect decay rate. That signal had never been emitted before. It started the same moment the sixth object initiated formation lock. For hours, the question of intent rippled across private observatory networks. Was this an accidental resonance, some natural byproduct of cometary chemistry, or was it a broadcast? Then, unexpectedly, the comet stopped shedding mass. No outgassing, no flares. It went inert, like a machine powering down after completing its function. This wasn't decay, it was stabilization. That's when the reflections changed. New spectral returns began to show uniform surface patches evenly distributed along the interior halo wall. They were brighter, smoother, and strangely structured. Comets aren't supposed to grow structures. They fragment, not evolve. Yet here was 3I Atlas, no longer breaking down, but building. Some researchers labelled this colonization. not in the classical science fiction sense of life forms taking over a body, but in a deeper, more symbolic way, the imprinting of intention onto raw material. Something was organising the dust, structuring the void, as if shaping the comet into a vessel, a container, or a message. And through it all, the sixth object remained in formation, silent, guiding. If this was the end of a natural process, it would look chaotic. But what we're seeing now is the opposite. It's elegant, predictive, purposeful. And maybe, just maybe, what we've been calling a comet is the scaffolding of something else entirely.